The universe is expanding at a rate that boggles the mind. Every second, the gap between distant galaxies stretches by thousands of miles. And here's the twist. It's not expanding into anything. There's no cosmic warehouse, no outer boundary, no larger container waiting to be filled. We're diving into one of the most mind-bending concepts in science, how space can emerge from nothing. We'll explore the mysterious force pulling reality apart and uncover why asking what the universe expands into is as baffling as asking what's north of the North Pole. Buckle up and join us on this cosmic adventure. Think about a balloon growing bigger in your living room. As you pump air into it, the rubber expands, pushing against the surrounding air. The balloon grows because there's space available. Your living room provides that environment, and this fits perfectly with our understanding of expansion in everyday life. But the universe finds this amusing. When astronomers say the universe expands, our brains conjure up the image of that balloon. We picture space spreading into some vast emptiness, a cosmic room awaiting its presence, and we believe there must be a border where our universe ceases and something else begins. This logic seems natural and straightforward. Yet physics challenges these comfortable assumptions because the universe isn't like that balloon. When it expands, it's not stretching into anything. There's no cosmic living room, no container, no external space. The universe is inventing the very concept of space as it grows. Imagine it this way. Try drawing a circle larger than your piece of paper. Instead of finding a bigger sheet, the paper itself expands to accommodate your circle. This seems impossible because in our reality, everything expands into something. Plants grow into the air, cities spread into the countryside, and ice extends over water. There's always a direction for expansion, a clear boundary. But what if you were both the paper and the drawing? Scientists unveiled this mind-boggling truth by observing distant galaxies. Edwin Hubble found that galaxies farther from us are moving away faster than those nearby. This might initially make us feel like we're the center of an explosion, with everything else rushing outward into emptiness. The truth is even weirder. Space itself is expanding. The galaxies aren't journeying through it. Rather, the space between them is increasing. Think about dots on an inflating balloon. As the balloon expands, the dots spread out without moving on its surface. The surface itself stretches. Each dot sees the others retreat, yet no dot is special or at the center. Now replace that balloon surface with the 3 dimensions of space we live in. The universe isn't expanding into anything because there isn't anything for it to expand into. It's crafting the very arena where expansion happens. This defies our intuition so radically that even the brightest scientists still grapple with it. Albert Einstein initially dismissed the idea. Yet this bewildering expansion is happening right now at a speed that defies imagination. But how do we know this bizarre process is real? The proof lies in tracking light as it gets warped by expanding space. When a distant galaxy sends light toward Earth, that light starts with a specific wavelength: blue, red, infrared. Each one is a unique signature, like a cosmic fingerprint. As this light travels through expanding space, something remarkable occurs. The space it traverses grows during its journey. Picture this. You're stepping on a moving walkway, but it keeps getting longer as you walk. Your steps are steady, yet the ground below is stretching. By the time you get to the end, you've covered way more ground than your steps would suggest. This is a lot like what happens to light. Instead of going further, its wavelength gets stretched. Blue light from a faraway galaxy reaches us looking red, not because the galaxy is zooming away like an ambulance changing its siren tune, but because the space it traveled through expanded over billions of years. Each light wave is stretched as the universe's fabric extends. This effect is known as cosmological redshift and shows that space itself can grow, regardless of the matter in it. Here's a mind-blowing figure. Light from the farthest observable galaxies has been stretched to 40 times its original wavelength. As this light journeyed through space, the universe expanded so much that what started as intense ultraviolet light now hits us as faint infrared heat. This 40-fold stretch means the universe grew by a factor of 40 during this light's travel. Consider this. The galaxy that beamed this ancient light to us appears tiny and faint through even our most powerful telescopes. Yet, when that light left its source, the universe was 40 times smaller than it is now. That galaxy was much nearer to where our Milky Way would soon take shape. The growth of space wasn't just a little, it was drastic and continual. But here's where things get even more bewildering. This stretching isn't happening somewhere far away. It's occurring everywhere. Right now, the space in this room is expanding. The space between your eyes and this screen is also trying to grow. You don't feel this expansion because the electromagnetic forces between atoms overpower the rate of expansion. This expansion only becomes evident across immense cosmic distances. There's no atomic force binding the space between galaxies, which allows it to expand freely, carrying galaxies like raisins in rising dough. The raisins don't move through the dough. The dough expands and spreads them apart. This is why the classic question, what is the universe expanding into, doesn't quite make sense. You're asking what the dough is growing into, but you're part of the dough itself. So, if space is stretching all around us, how far can we really see? We're inside this cosmic prison, and its walls are made of time. Each night, you gaze at the stars, feeling like the whole universe is on display above you. But here's the kicker. You're seeing less than 4% of what's really out there. You're confined in an unseen sphere. This sphere is around 46 billion light-years in radius. Beyond its edges lie more of the universe, with billions of galaxies and trillions of stars. Maybe even other versions of you are reading these words. But you won't ever lay eyes on any of that. Not with any telescope we can build, nor with any technology that could ever be developed. This isn't a trap of walls. It's one defined by the speed of light and the universe's age. Light takes time to get to us. Looking at the sun, you see it as it was 8 minutes ago. When you look at Alpha Centauri, you're seeing 4 years into the past. The Andromeda Galaxy, that's 2.5 million years ago. The farther you look, the further back in time you peek. Here's where the limits close in. The universe is 13.8 billion years old. This means the very oldest light reaching you has been on its way for 13.8 billion years. If there's a galaxy more than 13.8 billion light years away, it's almost like it doesn't exist to you. Its light just hasn't had enough time to reach you yet. But hang on, the situation is even trickier. Don't forget, space has been expanding all this time. That far-off galaxy was much closer to us when it first sent out the light we can see today. By the time this really old light lands on our telescopes, expansion has pushed that galaxy way past the 13.8 billion light-year point. Right now, it's actually sitting about 46 billion light-years away from us. This forms what feels like a cosmic jail cell for you. Everything beyond 46 billion light-years from Earth is part of what's known as the unobservable universe. You can't see it, you can't measure it, and you can't confirm it's real. Still, logic and numbers say it's got to be there, kind of like standing in a thick fog only 100 yards deep all around. You can make out a circle of land surrounding you, but you just know the world goes on past that fog. The observable universe is your foggy circle. while the real universe extends endlessly in every direction. Here's a mind-blowing number. If the universe is indeed infinite, your observable bubble contains 0% of everything that truly exists. 0. So what's waiting beyond our cosmic prison? The oldest light in the universe is racing toward you right now at 600 million miles per hour, carrying a message from the dawn of reality. This light has been in motion longer than Earth has existed, longer than it took for our solar system to form, and longer than it took for our galaxy to achieve its current shape. It set off on its journey back when the universe was a mere 380,000 years old. The cosmos was this roiling plasma ocean, so hot atoms couldn't even form, and we refer to this ancient radiation as the cosmic microwave background, and it's everywhere. Flip on an old television between channels, and about 1% of the static comes from this primeval light. You're literally seeing bits of creation flicker on your screen. This radiation fills every corner of space, streaming in from every direction at once. It's the oldest thing we can see with our eyes. What's profound about this discovery is that this light marks the edge of all that we can observe. Before that 380,000-year point after the Big Bang, the universe was opaque, much like trying to peer through the sun's surface. The early universe was like that everywhere, a dense fog of plasma that blocked all light. No photon could travel more than a few inches before slamming into charged particles and getting absorbed. But then something incredible happened. As the universe expanded, it cooled enough for protons and electrons to join up into the universe's first hydrogen atoms. Suddenly, the cosmic fog lifted and the universe became see-through. Light could at last trek freely through space. The first photons that slip through this cosmic parting are the ones arriving now as the microwave background. This event, named recombination, set up the ultimate boundary. You can't view anything beyond it, ever. Whatever took place in those first 380,000 years remains hidden forever, akin to trying to see through a brick wall that encloses the whole early universe. The cosmic microwave background is that wall, embodying the absolute limit of what's observable. Here's the truly mind-bending aspect. This horizon is on the move. Every passing second, light that's been journeying for 13.8 billion years plus a second hits us. Our observable universe expands by 1 light second every second. That's about 186,000 miles of fresh space coming into sight continuously. So every day, an extra 16 billion miles of the cosmos becomes visible. But growth gets complicated by expansion. While our view of the cosmos broadens, the actual gap to the source of that ancient starlight keeps widening because of cosmic expansion. That galaxy that sent out a photon 13 billion years back is now about 30 billion light years away. We're seeing it as it was long ago, not as it is now. This sets up a weird scenario. We're always spotting new bits of space, but the origins of that light are continually drifting farther from us. Imagine it's like watching a movie where someone walks away and the screen keeps getting bigger. The cosmic microwave background shows us the universe when it was smoother than a spotless mirror, with teeny temperature fluctuations of just a few millionths of a degree. Those minuscule differences in temperature would eventually evolve into everything around us today. But what about what's beyond that ancient boundary? Beyond the edges of what we can see lies more of exactly what we have already seen. It might sound pretty dull, but it's actually one of the most unnerving ideas in cosmology. If you could somehow zap yourself 47 billion light years away, way past your observable horizon, you'd land in a spot that looks an awful lot like here. More galaxies, stars, planets, maybe even more life. On the grand scale, the universe seems to be homogeneous. Homogeneous means looking the same everywhere, like a perfectly mixed cake batter with each spoonful exactly alike. Observations of the cosmic microwave background tell us the universe has this trait. The tiny temperature differences we find are smooth and steady all over the sky. This seamlessness hints at something profound about what extends beyond our sight. If our observable universe holds around 2 trillion galaxies, then a region of the same size just beyond our horizon would probably have roughly 2 trillion galaxies too. And the stretch beyond that would hold another 2 trillion, and so forth. This pattern might go on forever, or at least for much farther than we could ever wrap our brains around. But here's where it gets mind-bending. If space is genuinely limitless and uniform, then every possible way of arranging matter in any chunk of space must repeat somewhere. This isn't some mystical mumbo-jumbo, it's a mathematical certainty. With endless space and a limited number of ways to arrange a finite number of particles, repetition is bound to happen. Picture a deck of cards shuffled over and over infinitely. Sooner or later, you deal the same hand twice. The universe works like that, except it uses atoms instead of cards. This suggests there are other versions of you reading these words at this moment, literally, not figuratively. In spots so distant that their light will never find us, quantum mechanics has arranged matter in all possible ways, including those that mirror your exact state right now. There are versions of you who stopped reading this a while ago, versions that were never born, versions where Earth's entire history shifted in a whole other direction. The math implies these lookalikes exist at distances around 10 to the power of 10 to the power of 115 meters away, a number so huge that, if written out, the line of digits would span more space than our observable universe contains. Yet if the universe is infinite, even such immense distances remain finite. Somewhere out there, another version of you is grasping this same truth about yet another version even farther away. But wait, all this assumes the universe beyond our horizon matches what we see in our part. What if it doesn't? New observations hint that our cosmic nook could be anything but typical. It's like we're hanging out in a massive cosmic bubble, a part of space that's a bit less packed with galaxies than usual. If that's the case, heading past what we can currently see might lead us to parts of space dense with galaxies, black holes, more action, or maybe areas that are almost barren. Some theories hint that right after the universe began, it expanded at light speed, creating zones with wildly different traits, unique constants, particles, even completely different laws of physics. These other universes could be beyond our view, operating under systems that would make everything we know about physics useless. But amid all these theories, a more basic question pops up. What if our universe isn't endless? A never-ending universe spreading out is one of physics' strangest puzzles. How do you stretch infinity? Math says it can't be done. Add anything to infinity, and it's still infinity. Double infinity, still infinity. You can't increase something that's already everything. Yet we clearly see space expanding everywhere, even if it's endless in all directions. The key is to get what expansion actually means. The universe isn't getting bigger like that. Instead, the scale of space is getting larger. Imagine endless graph paper, each square an inch. Now stretch it until each square is 2 inches. It's still endless, with endless squares, but now every 2 points are farther apart. This is how cosmic expansion works. Infinity stays infinite, but space scales up. As space expands, distances between objects grow too. A galaxy that's 100 million light-years away today was once just 50 million light-years away. This brings up an unsettling thought. If the universe is boundless now, it was boundless when the Big Bang happened. The Big Bang didn't scatter matter and energy from one point. It was infinite space extending everywhere simultaneously. Try to picture it. The Big Bang was everywhere at once. No central spot, no boundaries, just infinite space starting to stretch and cool. Every spot in the universe could claim to be the expansion center because the growth looks the same everywhere. This infinite view clears up some cosmic riddles, but also introduces new ones. It makes sense why the universe seems uniform from any direction we look. In limitless space, that's the same everywhere. Every spot is the same. It also sheds light on why we don't find an edge or a center because none exist. Yet there's a thought-provoking question. If the universe holds infinite matter and energy, how isn't it infinitely dense? The clue is in realizing that density is about matter over volume. Even with both being infinite, that ratio can be finite. This translates into infinite matter spread across infinite space while keeping an average density, roughly 5 hydrogen atoms per cubic meter. Here's where it feels personal. In an endless universe, anything that's possible happens endlessly, not just repeated versions of you. Every storyline imaginable plays out somewhere in this majestic expanse. Every loss, every victory, every stunning moment, and every cruelty is part of the universe's tapestry. Feeling uneasy? Picture this: a universe that's finite. Now that's another can of worms. What's past its edge? How can space just end? What if you could somehow travel beyond it? These puzzling questions led scientists to lean towards infinite models, even with all their mind-boggling challenges. Recent studies of the cosmic microwave background suggest that our universe might be either infinite or so vast that any curve in space is impossible to see. The simplest way to look at it is to say space stretches out endlessly everywhere. So when you see the universe growing, it's not like building more rooms onto a house. It's more like stretching out an endless blanket. But what fuels this constant expansion if new space isn't technically being made? Space seems to be popping up from nowhere at a rate that would make any factory on Earth green with envy. Every passing second, the observable universe expands by about 10 to the power of 78 cubic meters. That's such an enormous number that counting up to it one number each second would take more time than the universe has been around, multiplied 1 billion times over. What's all this new space coming from? It arises from quantum vacuum. Quantum vacuum isn't the empty nothingness you'd expect. It's a bubbling brew of temporary particles appearing and vanishing almost instantly. This called quantum fluctuation process fills every inch of space with energy. Even in the best vacuum, these tiny activities never stop. And here's where it gets wild. This vacuum energy influences gravity. But different from matter, which pulls stuff together, vacuum energy pushes space apart. More space means more vacuum energy. More vacuum energy means more expansion. As space expands, there's even more room for new vacuum energy. This creates an ongoing cycle called inflation. In the universe's first split second, this process went nuts. Space expanded faster than light travels, but it wasn't things moving faster than light. It was that space itself was growing too quickly for light to catch up. Think of trying to walk on a treadmill that speeds up faster than you can run. In less than a blink of an eye, a space smaller than a proton ballooned to the size of a basketball. Sounds like sci-fi, right? But it's demanded by quantum mechanics. According to the uncertainty principle, energy can be briefly borrowed from the vacuum. During inflation, the universe borrowed an enormous amount of energy to create more space, then used the expansion to repay that debt. It's as if you took a loan to buy a machine that prints money, then used that money to repay the loan. Inflation worked so efficiently, it went too far. It should have stopped after solving some cosmic problems, but it didn't. Instead, it kept going, making way more space than we would have imagined. Our observable universe is just a small speck of a massive inflated region. Picture a balloon blown up to Earth's size, then looking at a tiny patch the size of a pinhead. That pinhead is our universe compared to the enormous region inflation created. But here's the mind-blowing part. This process hasn't stopped. Today's cosmic expansion isn't as rapid as inflation, but it runs on similar ideas. Dark energy, making up around 68% of everything, acts just like vacuum energy. It evenly fills space and pushes with a force that speeds up expansion. As the universe keeps growing, more dark energy appears to fill in the gaps. This completely goes against everything we know about conserving energy. You can't just create or destroy energy, yet it seems like expanding space continuously generates more dark energy. The answer to this puzzle lies in the fact that gravitational potential energy is negative. As the universe grows, matter spreads out, decreasing the gravitational binding energy. This negative energy is what balances out the positive energy of the new dark energy being created. So, the universe keeps a perfect energy balance while making infinite new space. This process will keep going on forever, or at least longer than we can even imagine. Every moment, there's more space, more dark energy, and faster expansion. The universe keeps expanding, not because it needs more space, but because the act of growing makes its own space. Yet this ongoing cosmic creativity is nothing compared to what went down in that very first split second. But what kind of proof do we have that this seemingly impossible event actually took place? Well, if you used to watch old television sets, there was proof hidden in their static for what might have been the most intense event in the universe's history. Back in 1964, two radio astronomers at Bell Labs were trying to figure out why their antenna was picking up some annoying background noise. Despite all their troubleshooting, cleaning off bird droppings and recalibrating everything, the unwelcome hiss stuck around. That noise was actually the echo of the universe's creation. Arno Penzias and Robert Wilson stumbled upon what's called the cosmic microwave background, which is basically the afterglow from the Big Bang that's been stretched and cooled over 13.8 billion years. This finding landed them a Nobel Prize and gave us the clearest evidence yet for the universe's expansion. This background radiation is crucial because its wavelength has the signature of cosmic expansion woven right into it. When this light first broke free from what was the early universe, it was vibrant, visible light at a scorching 3,000 degrees temperature. But as the universe expanded, the light's wavelength lengthened. What began as visible light waves turned into infrared radiation, then microwave, and eventually radio waves. By the time this ancient light hits us today, it's cooled to just 2.7 degrees above absolute zero. The cosmic microwave background is almost perfectly uniform, with just tiny fluctuations of 1 part in 100,000. This evenness shows how incredibly smooth the early universe was, spot on with inflation theory's predictions. Without the rapid expansion from inflation to smooth out any inconsistencies, we'd see wild temperature differences in the sky. But instead, we find near-perfect uniformity. Yet, it's those tiny variations that exist which tell a fascinating tale. They marked the quantum fluctuations that inflation blew up from tiny to gigantic proportions. Those minute ripples in the nascent universe eventually grew into galaxies, stars, and planets. You essentially exist because quantum uncertainty got massively amplified by cosmic expansion. High-tech satellites, such as the Cosmic Background Explorer and Planck, have mapped these temperature variations with incredible detail. The patterns we see fit inflation theory so well that we can figure out essential truths about the universe from this ancient light. We discover space is pretty much flat, find that ordinary matter is only about 5% of the universe, and gauge the cosmos's expansion rate and age with remarkable precision, all from analyzing static. But the cosmic microwave background also reveals something even deeper about expansion. This light shows us that everything we can see today was once packed into an area comparable to the size of a beach ball. When you look up at the night sky, every galaxy you spot, with even the most advanced telescopes used to be crammed into a space so small you could practically hug it. This wasn't like squeezing stuff into a little box. The very fabric of space was squished together. Think of it as if a beach ball was the universe itself, not just something inside it. There was no outside space around it. That compacted bit of space-time was what kicked off the expansion that led to the cosmos we know now. This realization brings up a puzzling question. If everything we see was once packed into such a tiny spot, what gave it the energy to expand so dramatically? The answer lies in a force that makes up more than 2/3 of the universe. Yet we can't see it at all. How do you even begin to detect something that's invisible yet everywhere? In 1998, two scientific teams wanted to find out how much the universe's growth was slowing. Instead, they made a groundbreaking discovery. It was speeding up. This earned them a Nobel Prize and flipped our understanding of the cosmos upside down. For years, people assumed that gravity would eventually put the brakes on expansion, causing everything to either slow down or start collapsing back together. Looking at distant supernovae, especially type Ia ones that burst with consistent brightness, seemed like a good way to measure this slowdown. These supernovae act like cosmic lighthouses. By seeing how bright they appear compared to how bright they should be, scientists can determine precise distances to their galaxies. But when they charted these distances with redshifts, they found something shocking. The distant supernovae were dimmer than expected, meaning they were farther away than what the standard model suggested. Somehow, space itself had stretched more during the time light traveled to us. The only logical explanation was that the expansion was accelerating, as if something was pushing space apart with growing force. They named this mysterious force dark energy, and it's all around us. Dark energy makes up about 68% of the universe's total mass energy, outweighing normal matter by over 13 times and even surpassing the mysterious dark matter that keeps galaxies together. Yet we still don't know what it is. Here's the weird part about dark energy. It doesn't clump up or thin out. While normal matter becomes less dense as space expands, like spreading out a fixed amount of matter over twice the area reduces the density. Dark energy keeps its density constant no matter how much space grows. With the universe expanding, more dark energy seems to pop up to fill the new space, meaning that its influence just keeps increasing over time. In the early universe, when everything was squeezed tightly together, matter and radiation were the main drivers of cosmic events. Dark energy was there, but it didn't matter much against the gravitational forces from all that clustered matter. Around 5 billion years ago, dark energy became the big player in shaping the universe's future. This roughly aligns with the formation of our solar system. Before then, Gravity was slowing the cosmic stretch. Afterwards, thanks to dark energy's kick, expansion began to speed up. We now live in an age where this acceleration rules the universe. Every day, dark energy's influence grows stronger and the pace of expansion picks up. While this change might seem minor within a human lifespan, it's incredibly significant when viewed over the vast timeline of the universe. In the distant future, dark energy will take over so much that faraway galaxies will speed away faster than light can reach them, disappearing from our view forever. But what exactly is this mysterious force steering the universe's fate? The top contender is vacuum energy, the tiny quantum fluctuations filling every spot in space. Quantum field theory suggests that empty space should hold vast amounts of energy. Yet, when scientists calculate it, they find a result that's 10 to the power of 120 times greater than what we actually see. This is one of the biggest mismatches in physics history. This either means we've got something seriously wrong about quantum mechanics, or there's something out there that's canceling most of the vacuum energy, just enough for cosmic acceleration. On the other hand, some ideas propose that dark energy is a new field spread across space, much like the electromagnetic field but with unique traits. Others think maybe gravity operates differently on cosmic scales. Truth is, we know about as little about dark energy as ancient humans knew about lightning. Yet this enigmatic force is pivotal to our universe's destiny, fueling an acceleration that notably picked up during an even wilder period of expansion. So, what's the deal when expansion outpaces light itself? Right after the Big Bang, there was this instant. The universe blew up faster than ever in the 13.8 billion years since. This phase, called cosmic inflation, pulled space so hard that some universe sections could no longer communicate. Spots that once exchanged light got split too far apart for light to ever bridge again. Here's where the universe bent its own rules. While nothing moves through space faster than light, space itself is exempt. During inflation, the distance between any two spots doubled in a blink, so fast that light couldn't keep up. Think of two ants on a balloon inflating so quickly they're forever apart, regardless of how fast they scurry. Now wrap your head around this. Inflation blew up the universe by a factor of at least 10 to the 26th power. That's like a grain of sand swelling to an observable universe's size. And this eruption took just about 10 to the minus 35 seconds. Comparatively, light covers roughly a foot in a nanosecond. During inflation, the universe grew by 20 orders of magnitude faster than light could cross a proton's width. Fueling this monumental expansion was the inflaton field, a hypothetical quantum field that filled all space. Unlike other quantum fields with minimal energy states dropping to zero, the inflaton field got stuck in a high-energy condition, a false vacuum. This spurred a temporary dark energy form, far stronger than anything we see today. While in this false vacuum state, the inflaton field drove an explosive expansion. Exponential growth starts off slow but ramps up in a big way. If you fold a piece of paper 42 times, its thickness would stretch from Earth to the Moon. The universe went through a similar but way more intense process called inflation. During this time, space doubled and doubled and doubled again almost instantly. This rapid growth solved big cosmological problems, but also introduced new mysteries. It explains why the cosmic microwave background appears so even across the sky. Without the quick smoothing effect of inflation, different sections of the universe would have wildly varying temperatures. Instead, we see surprising uniformity. Inflation also accounts for why space seems flat. Even if the universe started off curved, inflation stretched it out until any curvature became undetectable. Imagine blowing up a basketball so much that its surface looks flat to you. But perhaps inflation's most crucial impact ties into quantum mechanics. During this rapid expansion, tiny quantum ripples in the inflaton field stretched from microscopic to massive scales. These small energy fluctuations became the birthplace of galaxies, stars, and planets. Every structure we see in the universe has roots in quantum randomness amplified by inflation. This means the galaxy you're in, the star that warms your world, and the atoms in your body all owe their existence to quantum quirks at the universe's beginning. We're basically descended from quantum foam, but inflation suggests a chilling thought. If it happened once, it might happen again. The same quantum fields that started primordial inflation might still be out there, waiting for the right moment to trigger another bout of rapid expansion. This could start anywhere, anytime, without warning. A new inflation bubble expanding at light speed and obliterating everything as it grows. Inside such a bubble, everything as we know it would break down. Atoms would dissolve, and our natural laws would fail. We wouldn't see it coming. Yet, this scary thought is overshadowed by inflation's most puzzling idea. What if our universe is just one of many in an endless ocean of expanding realities? While you're reading this, countless other universes may be popping into existence, each with its own set of physical rules and possibilities for life. It's not science fiction, it's a logical outcome of inflation theory. If inflation happened once, quantum mechanics suggests it keeps happening across a larger multiverse. Random quantum changes can set off new inflation episodes anytime, anywhere. Each time a bubble universe forms, expanding, cooling, and developing its stars and galaxies. Our universe would be just one bubble among infinite others. Here's what makes this thought so unsettling. Every bubble universe might have different physical rules. Gravity might have different strength. Electrons could have different mass. The number of spatial dimensions might not be 3. Most of these universes would be inhospitable wastelands. In some, gravity could be so strong that stars instantly turn into black holes, while in others, it could be too weak for matter to clump together. Some might lack electromagnetic force, so chemistry, and therefore life, couldn't happen. Others may stay in eternal inflation, never cooling enough for atoms to form. Most bubble universes would be empty and barren. But in an infinite multiverse, every possibility, no matter how unlikely, happens somewhere. No matter how unlikely our universe's physical constants are, an infinite number of bubbles offers infinite chances for those exact constants to come together. We live in a cozy bubble that's just right for us, not because we're anything special, but simply because life can only exist in such places. This way of thinking, known as the anthropic principle, helps explain why our universe seems perfectly suited for life. We don't reside in a universe specifically designed for us. Instead, we're in one of those rare universes where beings like us can grow and ponder such things. The idea of a multiverse presents some deep philosophical questions, though. If countless universes exist, that means every possible event is happening somewhere out there. Every choice you never made, another version of you made it in a different bubble. Every disaster you dodged hits another you somewhere else. Every dream you didn't chase, it's a reality for another you somewhere. This multiverse means there are endless copies of everyone, everywhere, living out every possible scenario. With this endless repetition, the idea of being unique kind of loses its meaning. You aren't unique if there are infinite versions of you out there. Your choices don't make much difference when every choice is being lived out somewhere else. Your universe isn't one of a kind if there are countless similar universes around. However, we can't actually see or interact with these other bubble universes. They're beyond our cosmic reach, so their light never reaches us. and their gravitational pull doesn't affect us. Without being able to prove they exist or figure out how they work, this multiverse idea is hard to test. That's a big issue for scientists who believe untestable theories don't really count as science. Still, the math behind inflation suggests eternal growth and the popping up of new bubbles. The same equations explaining our universe's early expansion predict that this keeps happening throughout a larger multiverse. Accepting inflation means accepting what comes with it. Lately, observations are testing predictions of inflation more accurately. The cosmic microwave background shows faint patterns that match up impressively with inflation theory, lending more support to the concept of a multiverse. Our universe might be the evidence of infinite other ones. But this almost unbelievable idea assumes our universe has just the 3 space dimensions we're used to. New developments in physics hint that reality could be way stranger. What if there are expansions happening in directions we can't even perceive? The universe could be expanding in ways totally foreign to us. String theory, our boldest attempt to bring all of physics under one roof, proposes that instead of 3, there are 9 dimensions of space. Right now, 6 extra dimensions supposedly exist, curled up so tightly that even the tiniest particles can't detect them. These hidden dimensions might be growing right alongside the ones we're familiar with. Picture yourself as an ant on a garden hose. You can go forward or back along the hose, which feels like one-dimensional space. Yet the hose actually has 3 dimensions. The tiny, round dimension wrapping around it is just too small for you to notice. We could be in the same boat, aware only of 3 spatial dimensions, while 6 more lie beyond our senses. If these extra dimensions are real, they might explain what our universe expands into. Our 3-dimensional world might be stretching into a larger, higher-dimensional space. Similar to a balloon's surface expanding in the air, our universe could be a 3-dimensional layer spreading out in a 9-dimensional hyperspace. This idea, known as the brain world model, proposes that our entire universe could be a membrane floating within a larger dimensional space. Imagine that everything we see, every particle and force except for gravity, is stuck in a 3-dimensional space we can call a brain. Gravity, though, has the ability to slip out into extra dimensions, which might be why it feels weaker compared to other basic forces. The way our universe seems to be growing might be because our brain is stretching within a larger space. Here's where it gets really wild. Other brains might exist alongside ours in these extra dimensions. These parallel worlds might be just a tiny distance away, perhaps less than a millimeter, but in directions we can't move or point to. There might even be another version of you checking out these words, just a little distance away in a 4th dimension. Occasionally, these parallel brains might bump into each other, causing what we'd see as a Big Bang. That cosmic microwave background we observe, it might be the leftover glow from our brain smacking into another one in those extra dimensions. Such a collision would have released energy, fueling the rapid expansion of our universe and setting everything in motion. Every few trillion years, these brains could collide again, sparking another Big Bang and kicking off cosmic evolution all over again. But the math behind extra dimensions suggests even stranger ideas. Some theories propose that while our familiar 3 dimensions stay put, the extra dimensions might be expanding. From where we're standing, it seems like space is expanding, but really, it could be these hidden dimensions doing all the growing. It's like living on the surface of a balloon where the outside stays the same size while the inside grows. We can't detect the inside expansion because we're stuck on the surface. Other theories claim that while some dimensions grow, others shrink. Our universe might be stretching where we can see it, but shrinking in directions we can't perceive. Overall, the volume of space might stay the same, even though our slice of it looks like it's expanding. These ideas are still highly theoretical because we can't directly explore extra dimensions. The Large Hadron Collider, our top-notch particle accelerator, is on the hunt for hints of these dimensions, specifically through particles that might appear to vanish into this extra space. So far, no clues have turned up. This could mean the extra dimensions don't exist, or they're way more tightly nestled than our theories suggest. Still, string theory math insists that extra dimensions are essential to fully understand reality. If they do exist, they would redefine what cosmic expansion is all about. If someone asked what the universe is expanding into, the truth might be simple. It's spreading into dimensions we can't see or even fathom. But even without these extra dimensions, our usual three-dimensional space could still surprise us. What if space itself curves back, rendering the question of expansion moot? Picture the universe as a donut. An expansion might just mean the donut is getting plumper. It sounds outlandish until you grasp that the shape of space really dictates what expansion means. In a flat, endless universe, expansion just stretches space with no particular endpoint. However, in a curved, finite universe, expansion might just involve enlarging a closed shape that loops back on itself. Einstein's theory of general relativity leaves room for three possible shapes for space: flat like an endless piece of paper where parallel lines never meet, and a triangle's angles total exactly 180 degrees, or curved like a sphere where eventually parallel lines would meet and triangle angles sum up to more than 180 degrees. In a universe shaped this way, it would be like walking straight and somehow ending up back where you started. Or space might be bent more like a saddle, where parallel lines drift apart, and angles in triangles amount to less than 180 degrees. This type twists on forever, with negative curvature. According to what we currently see, our universe might be flat, or so nearly flat that any curve is too slight to notice. But flat doesn't always mean endless. Think of a flat piece of paper, which you could roll into a tube or connect to form a donut. It stays flat in small parts, yet overall it turns into something finite. Our universe might be the same. If space loops around itself, asking what it grows into doesn't make sense. A donut getting bigger doesn't grow into something else, it just becomes a larger donut. The outer surface increases, but it's not filling any extra space. This kind of wrapped universe could leave clues. In a donut-shaped universe, light might loop around and come back to its starting point, meaning we could see the same far-off galaxies showing up in different spots in the sky. The cosmic microwave background might have repeating designs from light having circled the universe numerous times. Scientists have searched for signs of this and found none so far. Either our universe is way bigger than the part we can see, or it doesn't loop around on scales we can detect. It might still be like a donut, just so massive that light hasn't gotten around it once yet. This becomes even trickier considering space and time as a four-dimensional blend. The universe's form isn't just about the three dimensions we see, it's about time too. Expansion stretches space and shifts the link between space and time across the cosmos. Back when the universe was crammed together, time ticked differently than today. Clocks back then would run at varied speeds. The idea of events happening together but far apart wouldn't mean the same. As space grows, time expands right along with it. This expansion of space and time causes effects that seem unreal. Far-off galaxies seem to zoom away from us faster than light, but they aren't really moving through space. Space itself is spreading them out, stretching time along with space. For those galaxies, they seem still while we appear to zoom off. This relativity makes expansion look identical from any spot in the universe. Everyone feels like they're at the center, watching everything else drift away. There's no special viewpoint, no real center, and no edge expanding into something else. The universe grows more into itself rather than turning into something larger. This idea about expansion leads to new mysteries about time's nature and how the passage of time might tie into space's growth in ways just being explored. What effect does stretching space have on the time dimension? As space pulls apart, time stretches too, changing everything about how the universe ages. When Einstein showed that space and time connect into a unified fabric termed space-time, he illustrated stretching one affects the other. As cosmic growth pulls space apart, it also stretches the rhythm of time throughout the cosmos. This isn't just a theoretical notion, it's visible reality. Picture looking through a telescope at a far-off galaxy. That galaxy seems to be drifting away from you thanks to cosmic expansion. Here's the kicker, though. Things happening over there look like they're unfolding in slow motion compared to what's going down around us. A supernova that takes 3 weeks to go through its light show in a nearby galaxy drags out a lot longer in a faraway one that's speeding away. This whole time-stretching thing happens because the light carrying news of those events gets stretched on its way to us. It's not just the light wavelengths that stretch. The time gaps between each pulse of light stretch too. It's like the universe is literally stretching time itself. In parts of space expanding fast compared to us, time seems to crawl. Here's a stat to put it into perspective. Light from galaxies at the very edge of what we can observe is redshifted about 10 times. That means those galaxies were zooming away at roughly 90% the speed of light when they sent out that light. Things in those galaxies play out 10 times slower than they do here. This makes for a wild scenario where the universe's age shifts depending on where you're at. From our viewpoint, the universe is 13.8 billion years old. But if you magically popped over to one of those far-off, fast-moving galaxies, our neck of the woods would seem much younger. Time's been stretched out by expansion. This stretching tells us something big about cosmic evolution. Back in the day, the early universe didn't just have more squished-together space. Time itself was packed more tightly, too. Stuff that takes billions of years now zoomed by in the dense early universe. The birth of the first stars, galaxies, and black holes all happened in a universe where time flowed differently than it does now. But expansion does more than just mess with time's tempo. It tweaks the whole idea of events lining up at the same time across the cosmos. In our daily life, it feels like if two things happen simultaneously, they happen at the same time everywhere. But relativity and cosmic expansion totally upend that idea. Events you think are happening at the same time, far-off observers would swear happened at different times. There's no universal now ticking throughout the universe. This breakdown of simultaneity means that asking what the universe's current activity looks like becomes pointless on a cosmic scale. Different observers paint now differently. The present isn't universal, it's local. As expansion speeds up, these time-warping effects get even more pronounced. Dark energy's hold grows over time, making space stretch faster and faster. This quickening space stretch also speeds up time stretching. Future galaxy-dwelling folks will see even more extreme time slowing when peering at distant galaxies. Eventually, expansion will stretch time so much that distant happenings will seem totally frozen. This ramping up of expansion prompts some pretty chilling thoughts about the universe's endgame. What happens when expansion gets so wild it overpowers every natural force? The universe is barreling toward a future so frigid and barren that no energetic processes will be left. This bleak fate, tagged as heat death, marks cosmic expansion's triumph over all else. As space keeps stretching, it will spread matter and energy so thin that the cosmos becomes a lifeless, evenly spread void at nearly absolute zero. The timeline for this cosmic curtain call is mind-bogglingly long. In about 100 billion years, the last stars will sputter out and fade into the void. New stars won't form anymore because the universe is expanding so much that matter gets too spread out for gravity to pull together new star-forming regions. This leads the universe into what's known as the degenerate era, dominated by the leftovers of dead stars. But that's just where the ending begins. In a staggering 10 to the power of 34 years, even protons will decay into lighter particles. The atoms that make everything from your body to planets and stars will just fall apart. Matter as we know it will be gone. Only electrons, positrons, and photons will exist in this ever-growing void. These timescales are mind-boggling. If we squashed the universe's current age into just 1 second, the proton decay period would stretch over a billion years. Still, this super long stretch of time is just a tiny slice of what lies ahead for the universe. About 10 to the power of 10 years from now, black holes will be the universe's last significant energy sources. Black holes slowly shrink by giving off Hawking radiation, converting their mass into particles and energy bit by bit. It takes longer than the universe's current age for a regular black hole to fully disappear. Those supermassive black holes hanging out at the centers of galaxies will last around 10 to the power of 10 years. Once the last black hole evaporates, the universe will hit perfect heat death. Temperatures will be the same everywhere, so no chemical reactions can occur, no computation will happen, and no life can survive. The cosmos will reach a balance of maximum entropy, a state where nothing exciting can ever take place again. With what we know of physics now, this fate seems unavoidable. Dark energy speeds up expansion, scattering matter and energy across ever-growing parts of space. Unless dark energy behaves differently, this expansion towards a cold, barren end will continue indefinitely. Yet this expansion brings an even more pressing problem for the distant future. As space gets stretched quicker, far-off galaxies move out of our observable universe. They're not being destroyed, just retreating so swiftly that their light won't reach us again. To us, they seem to fade into oblivion. In around 150 billion years, only the nearby group of galaxies will be visible. Future astronomers in the Milky Way will perceive a universe containing just a few dozen galaxies enveloped by emptiness. No signs of cosmic expansion will be visible to them because the expanding regions will be out of sight. These future scientists might think they're living in a small, unchanging universe. The cosmic microwave background, our biggest clue of the Big Bang, will vanish as well. Expansion will stretch this ancient radiation into undetectable long wavelengths. Future civilizations will miss out on the clues we had about cosmic beginnings. They'll live in a universe that looks completely different from ours today. But losing this cosmic view might still be better than what some theories suggest. If dark energy keeps getting stronger, the universe's expansion might accelerate to the point where it beats every force holding matter together. Gravity would fall apart first, then electromagnetic forces, then even the strong nuclear force binding protons and neutrons. The universe wouldn't just keep expanding, it would fracture from the inside. Yet, before we face this ultimate disaster, we need to understand the space that looks empty. What exactly fills this vacuum that harbors dark energy? Empty space isn't really empty. It's a boiling swirl of activity, more intense than the sun's core. On the tiniest levels, space is buzzing with virtual particles that pop in and out of existence so quickly they're impossible to catch in the act. Even though we can't see them, these phantom particles have real effects on the universe. This quantum foam is all around us, filling what looks like empty space. Imagine peering into this emptiness with a super-powered microscope, one that can zoom in smaller than an atomic nucleus. As you dive deeper, down to the Planck scale, around 10 to the power of minus 35 meters, space starts to look bumpy and chaotic. At this point, the smoothness of space-time unravels into a frothy mess of appearing and vanishing particles. These virtual particles borrow energy from the vacuum, following Heisenberg's uncertainty principle. The bigger the energy borrowed, the quicker they must pay it back by disappearing again. These exchanges happen so fast, it seems like they break the rules of energy conservation, but they're actually following the laws of quantum mechanics perfectly. The vacuum is buzzing with this hidden activity. Electron-positron pairs spring to life for about 10 to the power of minus 21 seconds before they vanish again. Even shorter-lived particle pairs involving heftier particles pop in and out even faster. Every imaginable type of virtual particle allowed by quantum field theory shows up in this seemingly empty space. These quantum blips have real, measurable effects in labs. Take the Casimir effect, for instance. When you place two metal plates a hair's width apart in a vacuum, virtual particles with wavelengths too big to fit between them stay outside, while longer wavelength particles keep exerting pressure from the outside, resulting in an observable force pushing the plates together. You can quite literally feel the squeeze of the quantum vacuum. But here's what's really mind-blowing. All these virtual particles should significantly affect the energy density of empty space. When physicists crunch the numbers to figure out how much energy the vacuum should contain, they get results so enormous that space would expand at a way faster rate than we see. The numbers say the vacuum should have 10 to the 120th power times more energy than dark energy, presenting a huge puzzle for theoretical physics. This leaves us with two options. Either our grasp of quantum mechanics is wrong, or some mysterious process is canceling out most of the vacuum energy. Cracking this vacuum catastrophe could unravel the mystery of dark energy. Maybe it's the tiny amount of vacuum energy that isn't canceled that becomes the dark energy we see speeding up cosmic expansion. Could the universe have a trick up its sleeve to suppress most of the quantum foam while letting just a bit stay active? Or maybe our ideas about vacuum energy are totally off base. Some alternative theories hint that empty space isn't empty in ways we're yet to grasp. Maybe unseen fields fill up the vacuum. Perhaps extra dimensions allow vacuum energy to seep away. The very idea of empty space might just be an illusion because of our limited viewpoint. Some theories even suggest space itself is composed of something. Loop quantum gravity suggests that space is made up of tiny, discrete blocks connected like atoms in a crystal. On the other hand, string theory imagines space coming to life from the dance of vibrating strings in higher dimensions. Both ideas see what looks like empty space as a detailed structure with internal complexity. If space is made up of pieces, then maybe its expansion is just those pieces stretching, instead of new empty areas popping up. Space isn't expanding into nothingness because it's something, though we don't fully get what it is yet. Our lack of understanding about space isn't as wild as the theories predicting what could happen if expansion speeds up beyond control. What if the stretching gets so intense it overpowers everything holding the universe together? In about 22 billion years, dark energy might grow so strong that it rips every atom apart, tearing the universe down to its simplest parts. This possible ending, known as the Big Rip, would be far harsher than heat death. Instead of a slow fade over trillions of years, the universe would destroy itself in a sudden burst of uncontrollable expansion, overpowering every natural force. The destruction would happen in a chilling sequence. Around 1 billion years before the Big Rip, dark energy might overthrow gravity's hold on galaxies. Galaxy clusters would fall apart as space stretches too swiftly for gravity to keep them connected. Individual galaxies would drift apart into endless space, isolated forever. 200 million years before the end, expansion could tear apart single galaxies. Stars would be flung from their galactic homes, lost in space. The Milky Way would come apart. Andromeda would break down. Each galaxy would turn into a bunch of separated stars, flying away as space stretches quicker than gravity can reel them in. 30 minutes before the Big Rip, expansion could break apart solar systems. Earth could be pulled away from the sun. The moon might spiral away from Earth. Each planet in every solar system across the universe could suddenly be alone in stretching space, heated only by its own internal warmth as its star drifts into darkness. The last half hour of existence would be a growing chaos. 90 seconds before the end, expansion might break molecular bonds, scattering atmospheric gases from every planet into space. Oceans could boil away, not because of heat, but because the space between water molecules would grow too fast for intermolecular forces to keep them together. Mere fractions of a second before the Big Rip, atomic nuclei could fall apart. The strong nuclear force binding protons and neutrons would finally give in to the unrelenting stretch of space. Every atomic nucleus in the universe could burst into separate protons and neutrons. The matter that formed stars, planets, and life could return to its basic elements. At the moment of the Big Rip, even space and time might unravel. Some theories suggest space can stretch only so far before distance itself breaks down. The metric defining measurements of lengths and time might become infinite, and causality might break. The universe wouldn't just cease, it would lose meaning entirely. This grim scenario depends on dark energy acting in a certain way. If dark energy stays the same, the Big Rip won't happen. The universe will keep stretching, gradually leading to heat death. Only if dark energy becomes stronger over time does the Big Rip become certain. Current observations show dark energy has been mostly constant throughout cosmic history, but the data isn't detailed enough to dismiss slow changes. Upcoming observations of far-off supernovae and other cosmic measurements will reveal if dark energy is getting stronger. Should it be increasing, we could figure out exactly when the Big Rip will happen. This calculation hinges on how swiftly dark energy is gaining. More cautious guesses put the Big Rip about 22 billion years ahead, while bolder models suggest it might be much earlier, possibly in just a few billion years. Neither scenario leaves much room for long-term cosmic strategies. Yet this ultimate breaking apart might not mean a complete end. There are theories suggesting the Big Rip could spark new cosmic inflation episodes, creating new universes from the remains of the old one. The ripping of space-time could give rise to new realities. But before grasping these cosmic conclusions, we need to delve into how scientists measure the expansion driving them. Cosmic expansion's tale started with observations, not theories. So, how do you measure something as enormous as the universe is stretching? Astronomers use exploding stars as cosmic measuring sticks, leveraging the brightness of star deaths to chart space's growth. The task seems daunting. How do you gauge distances to things billions of light years away? How do you tell if they're moving away from you? How do you differentiate between moving through space and space itself expanding? The solution comes from using the reliable behaviors of dying stars. Type Ia supernovae happen when white dwarfs gather too much matter from partner stars, exploding with nearly uniform brightness. These stellar blasts release the same energy amount anywhere in the universe, making them ideal standard candles for distance estimation. Here's how this works. When a Type Ia supernova blows up in a nearby galaxy, astronomers gauge its apparent brightness against the known inherent brightness of similar explosions. This difference tells them the precise distance of the explosion. Basic physics. Things seem dimmer the farther away they are. At the same time, they check the redshift of the host galaxy by studying light wavelengths from the blast. Redshift shows how much the light's wavelength stretched on its journey through expanding space. Higher redshift means the light passed through more expansion, showing both greater distance and an earlier cosmic time. By charting distance against redshift for hundreds of supernovae, astronomers map the universe's expansion history. If expansion was steady, the plot would form a straight line. If gravity was slowing expansion, distant supernovae would seem closer than expected. If expansion was speeding up, distant supernovae would look farther than anticipated. The data unmistakably indicates acceleration. Supernovae that exploded when the universe was younger appear dimmer than expected if expansion was constant. This means they're farther away than predicted, suggesting that space expanded more during the light's travel to Earth than anticipated. Dark energy has been speeding up expansion for billions of years, but figuring out cosmic expansion calls for more than just supernova. Astronomers implement various techniques to build the cosmic distance ladder, each step fine-tuned using the previous one. The base step uses parallax measurements for nearby stars. As Earth circles the Sun, nearby stars seem to shift against the backdrop of farther stars. This parallax angle, combined with Earth's orbit size, gives accurate distances to stars within a couple of hundred light-years. Parallax distances help us figure out the next step in the cosmic distance ladder. Cepheid variable stars. These stars pulse with periods that are directly tied to their true brightness. When astronomers measure how a cepheid pulses, they can determine its expected brightness. By comparing this to what they actually see, they get an idea of how far away it is. Cepheids are visible in galaxies up to about 100 million light-years away. They help set a baseline for measuring supernova distances, pushing our knowledge to billions of light-years. Each step relies on getting the previous ones right, so any mistakes can throw off the whole system. This has led to a major debate in cosmology. Different methods give slightly different numbers for the Hubble constant, which measures how fast the universe is stretching out. Local measurements suggest the universe expands at around 73 kilometers per second per megaparsec. On the other hand, measurements of the cosmic microwave background suggest a slower expansion of about 67 kilometers per second per megaparsec. This 6% difference might not sound like much, but it's a big deal in cosmology. There's something off. Either one of the methods is hiding unknown errors, or our whole understanding of how the universe has changed is wrong. Solving this issue might mean discovering new physics or finding errors in methods that have gone unnoticed for years. Despite this debate, both techniques agree on one key point: the universe is expanding, and that expansion is speeding up. But how do scientists turn these observations into math that describes the universe's growth? The whole history of the universe's expansion fits into a single mathematical function that shows how space stretches over time, also pointing to the universe's future. This is known as the scale factor, typically symbolized by the letter A. This straightforward variable tells us how distances change as the universe grows. When the scale factor doubles, all distances double, and when it triples, all distances triple. The scale factor makes the idea of cosmic expansion clear in a mathematical sense. Cosmologists usually set this scale factor to 1 for the present time. So way back when the universe was smaller, it was less than 1. Looking ahead, when the universe is larger, this factor will be more than 1. What's so effective about this model is how it links the observable universe to cosmic time. When observing a galaxy with redshift z, you're seeing it at a point when the scale factor was 1 plus z. A galaxy with redshift 1 was around when the scale factor was 0.5, or when the universe was half its current size. This lets astronomers piece together the universe's history from redshift data. The light from the cosmic microwave background shows a redshift of about 1090. This radiation dates back to when the scale factor was about 0.001, meaning the universe was a tiny fraction of its current size. The volume of space was 1 billion times smaller when that light was sent out. But the scale factor isn't just about the past. It also predicts how the universe will continue to expand by using Einstein's field equations. The speed of this expansion hinges on how the scale factor shifts over time. If it increases at a constant rate, so does the universe's expansion. If it speeds up faster, the expansion accelerates, and if slower, it decelerates. Observations show that the scale factor has been growing faster than linearly for the past 5 billion years, confirming that cosmic expansion is accelerating. The math outlines 3 possible futures, depending on the nature of dark energy. If dark energy stays constant, the scale factor will keep growing exponentially forever. The universe is expanding faster and faster, but this acceleration is heading toward a stable rate. This results in what's known as heat death, with matter becoming more spread out in the expanding universe. If dark energy gets stronger, the universe could expand at more than an exponential rate, culminating in the Big Rip, where it overpowers all forces. But if dark energy loses strength or turns negative, the universe might stop expanding and start contracting, leading to a big crunch. Right now, evidence points more toward the expansion scenario. The concept of the scale factor offers a deeper insight into cosmic expansion. The speed of expansion at any moment is purely tied to the universe's overall energy density at that time. Higher energy density causes faster expansion. Early on, when matter and radiation were densely packed, the energy density was immense, causing rapid expansion that gradually slowed as the universe grew and energy density lessened. About 5 billion years ago, dark energy took over, causing the expansion to speed up again. This scale factor encapsulates the entire shift from slowing down to speeding up. By matching theoretical curves with real-world data, scientists figure out the proportions of matter, radiation, and dark energy at different times. These findings show the universe currently consists of about 68% dark energy, 27% dark matter, and 5% normal matter. The scale factor approach also forecasts how these percentages will shift over time. As space expands, matter thins out, but dark energy's density remains constant. This means dark energy's role will become even more dominant. Eventually, dark energy will take over so completely that expansion will resemble pure exponential growth. But this way of understanding expansion arises from one of science's most significant mistakes. What happens when a brilliant idea accidentally nails the future? Albert Einstein added a component to his general relativity equations that he later dubbed his greatest error. Yet it was crucial for grasping the accelerating expansion we see today. Back in 1917, Einstein came across a hitch in his fresh theory of general relativity. The equations indicated the universe should be either expanding or shrinking, with no room for a static universe. But it was widely believed the universe was static and eternal, at least according to astronomers back then. The notion of a changing universe didn't make much sense. How could it expand? What would cause such expansion? Trusting the observational evidence, Einstein tweaked his equations by appending the cosmological constant, symbolized by the Greek letter lambda. This constant functioned like a repellent force balancing gravity's pull, keeping the universe static despite having matter in it. The cosmological constant represented the energy in a vacuum. Einstein saw this space energy as an innate feature of emptiness, creating a slight push outward to prevent gravitational collapse. It was enough to counterbalance attraction and keep the universe unchanged. For over 10 years, this seemed to work. Then Edwin Hubble found that galaxies are moving away from us. The universe wasn't static. It was expanding, just as Einstein's initial equations suggested. Thus, the observational evidence that once convinced Einstein to add the cosmological constant was wrong. Einstein later dismissed the cosmological constant, calling it his greatest mistake. If Einstein had stuck to his original equations instead of relying on faulty observations, he might have foreseen the universe's expansion well before Hubble did. In this scenario, he'd be known as the visionary scientist who, using just theoretical insights, predicted that space was stretching. Instead, he introduced a correction he later regretted, spending years trying to erase it from physics. But that wasn't the end. By 1998, astronomers found out that the universe's expansion was actually picking up speed. Something was pushing space apart, increasing in intensity, exactly what Einstein's once dismissed cosmological constant was meant for. What he thought was a mistake became key to grasping the universe's workings. This accelerating spread involves an odd kind of dark energy acting just like Einstein's cosmological constant, a steady energy permeating all of space, causing a sort of anti-gravity effect. Recent findings indicate that this cosmological constant is currently the best fit given the data. If true, it means Einstein's hunch about empty space harboring energy was incredibly intuitive. Even if he added it to his equations for all the wrong reasons, this insight turned out quite significant. The universe's cosmological constant, though extremely small, isn't zero. Every cubic centimeter of empty space holds about 10 to the power of minus 10 joules of dark energy. This might sound trivial, but when you think of the vastness of the universe, it amounts to more energy than all the matter and light combined. Although Einstein once thought this term was unnecessary, it actually plays a huge role in the evolution of the cosmos. However, it has introduced a challenge Einstein never saw coming. If empty space's energy propels acceleration, why is the amount so slight? According to quantum field theory, the vacuum energy should be 120 powers of 10, greater than what we observe. This vacuum catastrophe is among the weightiest puzzles in physics. Is our grasp of quantum mechanics seriously flawed? Or is there some unknown process that cancels out most of the vacuum energy, leaving just enough to drive the observed acceleration? Unlocking this mystery might demand brand new physics that even Einstein didn't conceive. Some theories suggest this dark energy might not be a constant. It could be a dynamic force changing over time. These alternatives could potentially solve the vacuum puzzle while still accounting for accelerated expansion, but so far, the data leans toward Einstein's initial guess about space's energy. The irony here is striking. Einstein added the constant to stop the universe from expanding, and then dismissed it when expansion came to light. In today's cosmology, it's back to explain why the universe is picking up speed. What he once called his biggest blunder has turned into an incredibly insightful prediction. Yet, even a mind like Einstein's was guided by observations that completely reshaped our understanding of the universe. So, what happens when an astronomer turns a telescope to the heavens and everything we thought we knew turns out wrong? In 1929, Edwin Hubble tirelessly measured the distances and speeds of remote galaxies and uncovered, almost by chance, that the universe was spreading out. At the Mount Wilson Observatory, with the world's largest telescope, Hubble aimed to settle a debate about spiral nebulae. Were these fuzzy patches part of our Milky Way, or were they separate galaxies at immense distances? His findings confirmed they were separate galaxies, but the real groundbreaking discovery lay elsewhere. Hubble used Cepheid variable stars to measure distances and discovered that these spiral galaxies were millions of light-years away, far beyond the Milky Way's limits. This discovery expanded our understanding from one galaxy to a universe filled with countless others. However, Hubble noticed an unusual pattern when comparing galaxy distances and velocities. Every galaxy was moving away from us. Not just a few or distant ones, but every single galaxy he measured showed redshifted light, meaning they were moving away from the Milky Way. This made it seem like Earth was at the center of a cosmic explosion. Even more intriguing, galaxies farther away seemed to be moving faster. If a galaxy was twice as far, it moved twice as fast. 3 times farther, 3 times faster. This pattern, known as Hubble's law, indicated a direct link between distance and velocity of recession. Initially, Hubble thought this pattern meant galaxies were moving through space. He pictured them racing away from us, like debris from an explosion in a still cosmic landscape. But this created big problems. If all galaxies were moving away from us, it suggested we were at the universe's center, contradicting the Copernican principle, which states that Earth has no special cosmic position. Why would we be in the center of everything? The solution came from realizing that space itself was expanding. Imagine dots on a balloon as it inflates. Every dot sees every other dot moving away. The farther apart they are, the faster they move apart. Yet no dot is special or at the center of this expansion, just like what Hubble observed. This insight turned Hubble's discovery from measuring galactic motion to proof of cosmic expansion. Galaxies aren't traveling through space. Space itself is stretching, moving galaxies along like raisins in rising bread dough. Hubble's law became the first evidence of the expanding universe. The constant in Hubble's law, known as the Hubble constant, describes the rate of space expansion. A larger constant means faster expansion, a smaller one means slower. Hubble's initial calculations suggested the universe was only 2 billion years old, which didn't sit right with geological evidence pointing to Earth being older. How could Earth predate the universe? The mistake was in Hubble's distance measurements. He mixed up 2 types of variable stars, leading to incorrect estimations of galactic distances. Once astronomers fixed these mistakes, the universe's age estimates comfortably exceeded Earth's age. Yet Hubble's distance velocity finding was still correct. Modern observations affirm that this expanding pattern fits Hubble's law with great precision across vast cosmic distances, from galaxies a few million light-years away to those billions of light-years distant. This consistency shows that expansion is a fundamental property of space. Hubble's work also established the first cosmic distance scale, allowing astronomers to map the universe in 3 dimensions. Before him, astronomy was mostly 2-dimensional, focused on celestial positions. After Hubble, cosmology became feasible, reshaping our view of humanity's place in the universe. We don't inhabit a static, eternal universe. We live in a universe that's constantly changing, a cosmos that started off hot and dense and has been cooling and spreading out ever since. Hubble's discoveries paved the way for the Big Bang theory, showing us that the universe is expanding. This led to a big question. Will this expansion go on forever, or will gravity eventually make it all come back together? The answer lies in how much matter the universe has, a mystery that has puzzled cosmologists for ages. Exactly how much stuff is needed to prevent infinite growth? There's a specific amount of matter that tells us whether the universe will keep expanding or eventually shrink back down. We're surprisingly close to this balance point in the cosmic scheme of things. This critical density is like having about 5 hydrogen atoms in every cubic meter of space, which sounds almost empty by everyday standards. Yet, this minuscule amount of matter, sprinkled across enormous expanses of space, ultimately dictates the fate of everything around us. What's happening is a tug of war between expansion and gravity. While expansion pushes galaxies apart and spreads matter thin across the universe, gravity tries to pull everything back together, potentially leading to collapse. The thing is, gravity's strength hinges on how much matter there is per unit of space. If there's more matter than what's needed for the critical density, gravity comes out on top. The expansion will slow, stop, and eventually reverse in a big crunch. But if there's less matter, expansion is the victor, and the universe grows endlessly, leading to a so-called heat death. If the universe nails the critical density, expansion will slow to almost nothing, but never entirely cease. This scenario is like a perfectly launched ball that keeps climbing forever while gradually slowing to a halt. For years, figuring out the universe's actual density was cosmologists' biggest quest. It seemed simple. Just tally up all the matter and see how much space it takes up. But reality is a lot trickier. Most of the universe's matter is invisible. Observations of how galaxies rotate show they have way more mass than visible stars account for. The speed at which stars orbit on the galaxy's edge needs at least 5 times more mass than observable matter can explain. This unseen mass is known as dark matter, which doesn't emit, absorb, or reflect light and only makes its presence felt through gravitational forces on visible stuff. This mysterious dark matter, although unseen, outweighs regular matter by more than 5 times. When cosmologists added dark matter into their calculations, they discovered the universe's density was about 30% of what's needed for critical density. This hinted at a universe destined to expand indefinitely, ending in heat death. But then dark energy entered the picture. This doesn't just boost the universe's total energy, but flips the whole expansion dynamic by introducing a repulsive gravitational effect. According to Einstein's equations, energy with negative pressure can cause acceleration in the universe's expansion. This discovery muddled up the concept of critical density. Conventionally, critical density assumes all matter and energy result in attraction, but dark energy, with its repulsive nature, accelerates expansion regardless of how much customary matter there is. Right now, experts think our universe is made up of roughly 27% dark matter, 68% dark energy, and only 5% regular matter. This blend puts us so close to what they call the critical density when you factor in the weird effects of dark energy's negative pressure. We seem to be sitting right on the fence between different possible shapes for the universe. This is what's known as the flatness problem in cosmology. Why are we so close to that critical density? Many cosmic evolution models show that the density either skyrockets beyond critical, leading to a fast collapse, or drops way below, resulting in endless empty expansion. Staying close to this critical density means the universe must have started with some seriously specific conditions. Cosmic inflation might just be the key to this flatness puzzle. During this inflationary burst, any original curves in the universe got stretched out super flat, leaving the universe nearly at critical density when inflation finished. This could explain why we're close to it now, but it's still a bit weird. We're living in a time when dark matter, dark energy, and ordinary matter are all having a pretty balanced effect on the universe's evolution. A while back, matter was running the show. In the future, dark energy will likely take over completely. We're in a short phase where everything is important. Maybe this is just a fluke due to selection bias. Perhaps intelligent life can only form when the universe's density is close to critical. Early times might have been way too chaotic, and later times might be too barren for building complex structures. We see this nearly critical density because only worlds close to critical can support observers. But that thinking kind of assumes we're one lonely universe out there, born from our own Big Bang and expanding ever since. What if countless other universes are also expanding, just like ours? Right now, as you're reading this, there could be trillions of other universes unfolding their own stories, each one born from its own Big Bang, moving in ways you can't even picture. These other universes wouldn't be super far off in our universe. They'd be in totally different dimensions that don't connect with ours. Each would have its own space and time setup, along with its own expansion tail. The multiverse might be growing in several layers at once. According to eternal inflation models, our visible universe is only a tiny part of a bigger, expanding area, and inflation never pauses. Quantum quirks keep sparking new inflation episodes all over, creating new universes that grow and move independently. Each one sets its own rules, constants, and growth patterns. While ours has been doing its thing for about 13.8 billion years, other universes might have been at it for trillions, or they might have just started a few million years ago. Some could expand way faster due to stronger dark energy, while others go slower with higher matter densities. A few might already have crumbled in big crunches, their whole lifetimes over in a blink. Others could be nearing a big rip, where expansion tears everything apart. Each universe expands differently, but the multiverse idea doesn't stop there. It just keeps growing. Some theories say that each time a quantum measurement happens, it kicks off parallel realities where all sorts of different outcomes take place. In this many worlds viewpoint, the universe keeps on splitting into different versions of itself, each carrying on with its own unique quantum journey. Imagine countless parallel universes popping into existence every moment. Most would look a lot like ours, just with some tiny quantum details being different. But some would be way out there, thanks to a completely different sequence of quantum events. In certain parallel worlds, dark energy might amp up, making the universe blow up faster. In others, dark energy could lose its grip, giving gravity the chance to put on the brakes. In the vastness of the quantum multiverse, every possible expansion scenario could unfold. That means you've got alternate versions of yourself out there, dealing with every imaginable cosmic twist of fate. Some are cruising toward a universe that's burning out, while others are facing the prospect of everything being torn apart. Then, there are those in universes that might eventually shrink back down. The way space expands affects every possible reality out there. But when you start thinking about parallel universes, it really gets you questioning the whole idea of cosmic expansion. With infinite universes each expanding in their own way, does our universe's journey even matter? Some folks say that in the grand scheme of the multiverse, our universe's destiny just doesn't count for much. Sure, our cosmos might be heading for a big chill, But a never-ending number of alternate yous are still hanging out in universes where things expand differently. But on the flip side, some argue that each universe holds significance for those living in it, no matter how many parallel versions exist. And then there's the mind-bending complexity of what expansion means. In one universe, expansion covers the whole spread of space. But in a multiverse, it might hint at just one layer of a much bigger picture. Our space could be growing while the bigger multiverse doesn't budge. Or maybe the multiverse itself is broadening in ways we can't even wrap our heads around. Recently, scientists have been hunting for traces of parallel universes by scanning the cosmic microwave background for faint patterns that might show we collided with other cosmic bubbles. So far, zilch. Still, not finding evidence doesn't mean those other realities aren't out there. The scale is mind-blowingly vast, and the effects are so tiny, catching other universes might always be out of reach. We could be left puzzling over parallel expansions without a single proof. Yet even if we never spot these alternate realities, our own universe's expansion raises huge questions about information and meaning in a universe that just keeps getting bigger. What happens to our knowledge, memories, and identity as the space holding them stretches off into infinity? Think about every thought you've had, every memory, every scrap of info that makes you you. They're all wrapped up in specific setups of matter and energy in space, and as the universe expands, those setups are slowly unraveling. This creates a mind-boggling paradox in physics. They say information can't be erased, but expansion seems to spread it so far that getting it back would be impossible. Enter the holographic principle. Theoretical physics hints that all the info squeezed into a chunk of space can be encoded on the surface that surrounds it. Like a hologram that packs 3D images into a 2D surface, maybe the universe stores all its data on cosmic edges. But as space keeps getting bigger, the surface area of any boundary also grows. So, as the universe keeps stretching out, the capacity to pack information onto these cosmic surfaces grows right along with it. So the universe's ability to store information keeps ramping up over time. That means more complex structures can pop up, even as expansion makes existing info spread out thinner. But, with this growth, new challenges appear. The stuff that makes you is stored in the specific pattern of neural connections in your brain. These patterns rely on exact arrangements of molecules, which in turn lean on precise configurations of atoms. As the universe grows, these setups drift apart. Over long cosmic periods, this expansion would eventually separate the atoms in your brain to distances that outsize today's galaxies. The thoughts and patterns that define you would scatter so broadly that putting them back together would be impossible. You'd essentially become part of the ever-expanding emptiness. Yet, quantum mechanics throws a twist in the tale. Quantum states that store information might not care about specific locations in space, but about how particles relate to each other, no matter how far apart they are. Thanks to quantum entanglement, particles can stay linked instantly, regardless of the gap between them. Even if expansion spreads entangled particles billions of light years apart, their quantum states stick together. The information held in these connections could go on surviving forever, no matter the vast distances. This means those information patterns might still hang around, even as the things carrying them get scattered all over the growing universe. Yet, expansion hits us with another info hurdle: the loss of communication between faraway regions. As space expands, bits that swap info back and forth will eventually drift apart so swiftly that light can't make the trip between them anymore. These zones lose the ability to communicate, becoming helplessly disconnected. Despite quantum entanglement, the info gets stuck within isolated cosmic zones. Each of these zones holds a limited amount of info, trapped forever without a chance of mingling with other islands of information. The sum of knowledge in the observable universe gets split into separated areas. This breaking up could mean a form of info loss, clashing with the core rules of quantum mechanics. The answer might lie in seeing how info works on several levels at once. Local info patterns might fade due to expansion, but bigger picture patterns could come into being on a massive cosmic scale. The very tail of expansion captures info. Every tiny detail about how space has ballooned since the Big Bang is tucked away in the cosmic microwave background, the spread of galaxies, and the layout of space-time itself. This cosmic info might persist, even as smaller patterns fade away. The universe might become its own record-keeping system. Yet, even this epic info faces a major threat from speeding expansion. As dark energy pushes the universe to grow even faster, the cosmic microwave background will eventually shift to wavelengths we can't detect. Future beings won't be able to see any signs pointing to the universe's beginning. With accelerating expansion, any trace of the Big Bang might vanish. Civilizations that pop up way in the future could think they live in constant empty universes without a beginning or evolution. The proof of their cosmic ancestry will have disappeared into the stretch of space. This brings up deep questions about whether meaning can last in an ever-growing universe. If all info dissolves into inaccessibility because of expansion, do the events in cosmic history still matter? Maybe getting there is more important than where you end up. The patterns of information that briefly pop up during the universe's expansion, like consciousness or civilization, might find their worth in merely existing for a moment rather than sticking around forever. But even these philosophical comforts might not matter in a universe where expansion eventually wipes out any beings who could ponder these issues. So, when there's no one left to comprehend things, what becomes of comprehension? 150 billion years down the road, astronomers will gaze at a night sky and see a universe that seems utterly different from today's, leading them to completely wrong ideas about cosmic history. These future scientists will exist in a universe that looks small, unchanging, and eternal. They won't see any sign of expansion, remnants of the Big Bang, or clues that billions of galaxies once stretched across the cosmos around them. The accelerating expansion will erase the proof that once helped us grasp cosmic evolution. By that far-off time, dark energy will have shoved most galaxies beyond the cosmic horizon. The light from these galaxies will shift to wavelengths so long they'll become undetectable. To future eyes, these galaxies will simply fade from sight. Only our local group of galaxies will be visible. These astronomers will observe a universe that seems to include just a few galaxies amid vast emptiness. The Milky Way, Andromeda, and their satellite galaxies will morph into one large elliptical galaxy, drifting alone. This galaxy will look like the entirety of the universe. The cosmic microwave background, our clearest proof of the Big Bang, will also vanish. Expansion will stretch this old radiation to wavelengths longer than the entire observable universe. Future technology won't pick up any trace of this early light. Without the microwave background, tomorrow's cosmologists won't have evidence that the universe ever had a beginning. The redshift distance link that clued us into expansion will be immeasurable. With no far-off galaxies to see, future astronomers can't uncover Hubble's law. They'll never realize that space is expanding. Their universe will seem totally static. These future thinkers might dream up wholly different theories about the cosmos. They might believe their solitary giant galaxy has always existed in an infinite, stagnant void. They might not imagine their universe once bustled with galaxies zooming apart due to cosmic expansion. They'll find themselves in a universe stripped of its history. But the loss of cosmic understanding goes even further. Future observers will also miss out on knowledge about the physics that shaped early cosmic evolution. The nuclear reactions that created the first elements will have wrapped up billions of years earlier. Proof of Big Bang. Nucleosynthesis will linger only in the chemical makeup of ancient stars. These future populations will encounter a deep crisis in understanding. They'll have the same intelligence and tech abilities as people now, but they'll look at a universe that hints little about its true nature. Their scientific methods will work flawlessly, yet lead them astray about reality. This brings unsettling thoughts about our own cosmic knowledge. Are we being tricked by seeing the universe at a certain era? Are we missing key evidence that was visible to past watchers but already faded out? Maybe civilizations that existed soon after the Big Bang could witness phenomena forever unseen by us. This idea also links to the very future of cosmic expansion itself. As space keeps on stretching, even the processes keeping life going will eventually grind to a halt. Star births will stop when the gas is too thinly spread to clump together under gravity. The stars already shining will burn through their fuel and dim into shadows. Black holes will eventually vanish due to Hawking radiation, leaving just elementary particles scattered through the immense void. The universe will edge closer to its final stage: complete heat death. Any beings who somehow persist until that far-off era will find themselves in a cosmos even trickier than what future astronomers will face. They won't see stars, galaxies, or any kind of structure. They might think their universe is just a few particles floating in endless empty space. They'll have no hint that once upon a time, their reality was packed with trillions of galaxies. This journey from richness to emptiness is what ultimately happens when you wonder what the universe expands into. People often think that expansion needs a place to go, a purpose, or a final state to make the whole journey worthwhile. But maybe expansion is its own reason, a process that gives birth to temporary complexities rather than aiming for a permanent finish line. The structures we see today, galaxies, planets, life itself, all exist because expansion makes a dynamic backdrop that lets them spring up. Without expansion, the universe would either crash into itself immediately or stay locked in eternal simplicity. Expansion sets the stage for the cosmic drama to play out. Yet this realization circles us back to that big question we started with. In a universe that creates its own space, its own time, its stage, what does it even mean to ask what it expands into? Questioning what the universe is expanding into is like pondering what's north of the North Pole. Understanding why this is the case reveals some crucial truths about reality itself. When you're curious about what the universe expands into, you're assuming something that seems logical but isn't possible. You're imagining expansion needs some pre-existing space to move into, like a balloon needing air or a city needing a countryside. But a universe isn't like a balloon. It's space itself. When space expands, it doesn't move into something else. It defines the concept of else as it grows. There's no outside context because the universe sets what outside means. This isn't down to the limits of human language or a lack of scientific creativity. It's a basic aspect of reality. Before expansion, terms like into and outside didn't even exist. Expansion isn't just about making more space. It creates the very logic that makes sense of spatial relationships. The universe doesn't move into something because it defines what something is as it spreads. Consider it this way. Asking what the universe expands into is like asking what caused the initial cause or what's holding everything. The question presupposes categories that only make sense after whatever you're asking about has already taken place. The universe expands by becoming more universe, not by growing into non-universe. This shifts our view of cosmic expansion from a basic process to something much deeper. Expansion isn't just about the universe getting larger. It's about reality conjuring itself into being. Each new cubic inch of space that appears creates fresh possibilities for matter, energy, structure, and complexity. The universe isn't expanding toward some set goal. It's expanding into the boundless potential of what might be. We're not just riding a cosmic ride heading toward a final stop. We're part of the process that lets reality make itself. Our consciousness, our questions, and our urgent need to grasp what the universe is spreading into all show how the universe is getting to know itself. The expansion we see isn't separate from us. We are the expansion. We embody space, time, matter, and energy, forming patterns so complex that we ponder our existence. This view solves the puzzle of cosmic expansion, but unveils an even deeper mystery. If the universe creates its own space and time, becoming both the stage and the audience, then what we consider existence might be stranger than any science fiction tale. We could be inside a self-creating endless cycle with no start or finish, no border or purpose, other than the wondrous fact of its constant unfolding. The universe unfolds within itself, making room for endless possibilities. That includes the possibility of beings like us, who can appreciate the whole incredible and beautiful process. The question of what the universe expands into took us on a journey through inflation and dark energy, multiverses, quantum foam, and the beginning and end of time itself. Yet, the deepest answer was always right there. The universe expands into mystery, into wonder, into an endless capacity for more questions, discoveries, and moments where we understand we are part of something much bigger than us, yet closely connected to our tiniest thoughts. We are the universe questioning what it spreads into. We are the expansion wondering where it's headed. We are space and time waking up to their own being, astonished at the limitless creativity of the process that brought us here. And with that understanding, the question shifts from a puzzle needing a solution to a celebration of the magnificent enigma of existence itself.